This is WFNP 88.7 Rosendale. Welcome to Curiosities of the Cosmos. I'm your host, Allyson Sheneman. Today I brought on Jacob Beadle to talk about lasers and particles. Welcome to Curiosities of the Cosmos with Allyson Sheneman. My guest today is Jacob Beadle, a physics and astronomy double major. He has done research pertaining to optical physics and mathematics, and in June he is starting an MS/internship program with the University of Oregon's Knight campus on the optical materials and devices track. Jacob, thanks for coming on the show today.
Yeah, no problem. Thanks for having me.
For our listeners, Jacob and I met through working on a similar research team, like as a part of the same team, but on different projects, I guess is how I would explain it. And so we attended a conference together where we presented some of that work and got to do some networking and stuff in Washington State. It was like genuinely one of my favorite trips of all time.
So
it
fun.
Was so awesome. Yeah, that's just been a blast. And so I'm really excited to have you on the show. I feel like we're going to have wonderful conversations. I'm very excited about it.
Yeah, hopefully it'll be a good time.
Yeah. So yeah, can you just start out by explaining a little bit of the research projects that you've been on, context for those, maybe how you got onto those teams, what the projects are?
Yeah, so my first ever research experience was with Dr. Catherine Hearn, who's a professor here at SUNY New Paltz. She does the optics, all the optics classes. She does the optics research here. She's one of the main research professors. I mean, the other professors do research here, but for the most part, the most research is done by Dr. Catherine Hearn. So she kind of reached out to the whole department, all of the kids here, and said, hey, who wants to join my team? Who wants to get involved with the research here? And I, sent an email almost immediately because I was like, I need something. I need some experience. So I got in on that. And the first thing that I did was with an optical tweezer. Essentially what that is think of a normal tweezer. So you have something very small, just grasped with the light instead of metal. So in this case, the light focuses down to a very, very small beam waist is what we call it. So think of it as like the light crossing at a middle section. And at that middle section, you have something held within that beam waist. In my case, it was either a polystyrene microsphere, so just a little tiny ball at the scale of a micrometer or something, or a Dello Vibrio bacteriovorus, which Allyson has worked with, which is it's a little bacteria that feeds on E. coli. And yeah, we would, do some tests on those. I was trying to find the trap stiffness of the laser, which just means essentially it's like the stiffness that the laser is holding that object in the center. And then my second thing that I did was also with the tweezer. It was using calcite, and I was trying to use different light modes. So the laser itself can look different ways. That's the best way to describe laser modes. So it can either look really, really nice and circular when you look at it through a camera. Let's say you're shining the light directly into a camera. Then it can look really circular and nice and full. Or it can have like a hole in the center is what it looks like. And then there's like a ring. So think of it like a halo that appears on the camera when you shine it in, right? So that's like kind of the difference between like a Laguerre-Gauss mode versus a Gaussian mode, right? Those words might mean nothing to you. That's absolutely okay. But the point is that's kind of what I was doing. I was creating different modes and experimenting with them with calcite. And then phase shifting them. So if you're familiar with any mathematics, phase shifting is just when you take a wave of some sort and think of it on like an XY graph. You're just shifting it, like say like left or right. So with a light wave, because waves have particle wave duality, you can shift the wave, its components, the same way you do with a normal graph. You just shift a normal function. You just shift it like left or right or whatever, up or down, things like that. It's the most simple way to describe it. So I was doing that with the calcite. Then I went to a Harrington STEM lecture, which is one of these things that my school does, SUNY New Paltz does, which a couple days in the semester, they'll invite professors over from other institutions and researchers, and they'll invite all the students and staff to come look at their research progress and things like that. So I went to this Harrington STEM lecture, and a professor named Dr. Vincent Martinez from Hunter College in New York City was presenting his research. It was about turbulence, and I was very interested in turbulence. I mean, at the time, it was just because I was dealing with Brownian motion, and Brownian motion was cool to me. Not directly related with turbulence, but I was thinking like, oh, what if, the Brownian motion caused by the particles that were being trapped somehow creates turbulence within my fluid mediums. Brownian motion, which I just realized I didn't explain, Brownian motion is just the inherent movement of particles. And what that means is, so think of like the atomic level. Things move around a lot. We call this temperature. Just the inherent kind of movement of particles within the system because of their energy. So things are bouncing off of each other. Everything's moving around, right? So Brownian motion isn't temperature, but it is kind of caused by temperature. Things moving around and bouncing off of each other, and moving around within the mediums that they're in, whatever, right? So basically, in my optical traps that I was using, there was a lot of Brownian motion. Just I wasn't moving it purposefully. Just these particles would move around because of the Brownian motion. Anyway, I asked this professor about if Brownian motion could cause turbulence, and he said, maybe there's something there. It's just that at very small levels, turbulence kind of fades out. It kind of dissipates to a certain extent that it's not readable, and also so small that it's almost like a limit. So it fades away to zero, is the way that he described it. So maybe it wasn't exactly, linked turbulence to Brownian motion, but at least I kind of asked a good question. So
sometimes that's all it takes.
Sometimes that's all it takes. So yeah, I mean, I asked a good question, and I got him to email me his slides for the talk, which, was good. It got me in the door. And then I just asked him if there was any other research that he was doing with Hunter College that I could get in on, or if Hunter College itself was just doing anything I could apply to. And he said, well, there's not anything official that I could apply to, but he could interview me for his research team. So that's kind of just how simple as it was. He didn't really ask for any requirements, GPA or anything. I mean, he already knew what my research was, so he just he interviewed me for the team, and then I seemed to be a good fit for him. So now we've been doing research ever since. I'm still involved in that research. It's very fun. I'm doing parameter estimation for partial differential equations. It's very fun. Using PINs, physics-informed neural networks. So yeah, that is good. I'm thinking, right now, in terms of optics, I'm doing a project in which I'm heating up magnets and seeing how the temperature affects the magnetic field. This is my senior research project for physics. Just came up with this project because I really was interested in Ising models and things like that, which is basically just a model of how magnetic poles within magnets kind of flip and become orderly in the kind of model of that system. And, well, I think you can make Ising models for other things, but one of the most famous Ising models is for kind of the dipole moments of a magnet. And, I became very interested in that whole system. And so I wanted to do something involving magnets, and this is the thing I came up with. Basically you heat up a magnet, and you see how when you increase temperature, if the magnetic field decreases, and you can notice that, and which it does. So I've found that it's very good. And that's my research experience.
A little resume for us.
little resume, yeah.
Yeah, that's awesome. I think, first of all, it's something that I've just noticed as you were talking about it, that I feel like so many people get bogged down in details of research that it can be hard to make research projects that are really complicated, concise like that. And so I feel like you did a great job of making it like, if I wasn't taking any physics classes, any astronomy classes, I imagine everything you just said I could probably follow.
Okay, good.
And that is really hard to do. So just a little shout out there.
Okay, good.
Because I feel like, it's hard to know like what to say, what to explain. And I like when you catch yourself saying a big word, you're like, okay. And before I explain what that does for the project, let me explain what that is.
Right,
yeah, it can get complicated like that. But so most of your research is in optics or mathematics, right?
Right. Yeah. I mean, all of my research is in optics and mathematics. Most of it isn't just straight the optical side of things. The mathematics is basically just like computational physics to some extent. I mean, it's more math than I would say physics, that side of things. But yeah, most of it is in optics, for sure.
Is that something that you, like, once you decided that you were doing physics and astronomy, is that something that you knew to expect that you were going to be interested in? Or is that something that you kind of just, like, you even said a little that, like, the professor who does research here, Dr. Catherine Hearn, like, she's the professor to do research with, that she sent out an email being like, does anybody want to do research? And you're just like, that's the thing that I'll do. Did you know that optics was something you were going to be interested in, or did the interest kind of come through the project?
Yeah, I mean, that's a good question. I think because initially, at the start of my college career, I was like totally into astronomy. That's why. So my 2 degrees are astronomy and physics. So it's like I was very much into like the observational astronomy aspect, very much into like, I'm just going to be sitting on a mountain or a hill somewhere, some telescope, in like Chile, just like doing observational astronomy. But eventually I became more interested in the applied physics kind of road. And as that developed, I was also doing more things in optics with Dr. Catherine Hearn. I feel like it kind of developed at the same time. It wasn't just because it was the research that I was in that I became interested. I think it was also just like because of the classes I was taking, because I was thinking a lot more about what I wanted to do as an actual career when I got to like my junior and senior years of college. And when I started to think about those things, I was like, okay, I want to get more into applied physics. And optics is really just one of those things that is so broad of a category within applied physics right now. You can go in so many places. So I think it just makes sense for me to go the optics route because of my experience, but also because of just wanting to do applied physics. But it did kind of come out of nowhere to some aspect because of that shift, where at first I was just so into astronomy and astronomy alone, and now it's like, okay, because optics was introduced to me, I guess, by Hearn, and then also, going to the conference, going and doing all these other things, that it was like, okay, now this is the road I'm going to take for sure. Yeah.
Gotcha. Yeah, I feel like something that I hear in you saying that is this, like, being able to be interested in just about anything and, like, letting things come to you more. And I think that's something that I've found really beneficial as I've started to implement that, like, I guess, practice into my own, like, mindset, to be able to, like, whatever research comes to me, I'm going to be excited about. Like, that is just something I'm not willing to compromise on about myself, that I want to be excited about any research that comes to me, and therefore I will be. And so for me, like, being a part of an optics team was very much so, like, out of left field. I was not expecting to do optics. I was not expecting to like optics.
But you did bio, right? So
yeah, it was a biophysics project mostly. And I think the reason that I even signed up for it originally as my first research project ever was to do the bio side of things. And I think I surprised myself by how much I liked both research in general and also optics and physics and the rest of it. And so I feel like, to me, that was the beginning of that cultivation of the practice of being able to be interested in anything that comes to me, where after that, any research project that I could be a part of, I was signing myself up for immediately. Because I think it's really important to just, like, especially when you're doing research and you're trying to make a career out of science, to be able to take any project that falls on your plate and make something exciting about it.
Yeah, I mean, with the math research that I'm currently doing, I mean, when I started it, I had taken one PDE class that was mostly memorization.
What's PDE for people who might not know?
I had said partial differential equations earlier, but I know the acronym obviously doesn't come easily. But so when I had started this research, it really was definitely something out of left field, because I'm not a mathematician. I mean, I know a lot of people, they lump math in with physics.
Yeah.
Because they're like, oh, there's so much math involved, and oh, quantum mechanics is, ridiculous, and I can't imagine. I think, when you study enough of physics and you study enough of math, there comes a distinction at a high level where you understand that the mathematicians are wizards, and the physicists are little babies.
Right.
And I say that as someone who studies physics. And obviously they're just in real talk, they're just different fields.
Sure.
And the physicists don't use math in the same way. We don't want to. Where the mathematicians, they'll go above and beyond to develop math as a language, not necessarily for things that exist in the real world. They'll go and just look at how functions go into each other, look at infinities where they don't exist in nature necessarily, but just, where they could exist potentially in the future. And we need mathematicians for that reason, but, in physics, we don't do that. We just look for the natural aspect of it. But that being said, I'm on this math research team, and we're analyzing partial differential equations that do exist in nature. And that's where it comes in the physical side of things. But we're analyzing them to an extent in which I really have to know the partial differential equation.
Yeah.
And that was hard for me. It still is hard for me to really understand these equations because, even the physicists that made these equations were more mathematician than they were physicists. So... and then I'm also trying to learn the computational side. I'm trying to learn the Python coding and all these. And learning Python is unique because it's not just, I'm going to learn Python as a language, right? Because that would be hard enough. But the real issue is that you have 1,000 different libraries and 1,000 different packages within Python that you could potentially use for something. And when doing research like this, you're constantly jumping around package to package, library to library. And by library, I usually mean GitHub library. So GitHub is a repository that a lot of organizations and things use in order to get like code, let's say. So you can, if you're a developer or if you're a researcher, you can upload your code to a repository, and then someone else can come and take that code and then use it for your own needs. It's a public repository, so I go to all these libraries and it's great. I can scavenge the code from public sources, but then now I'm having to use packages and things that those libraries use. So not only am I using different code, but I'm using different packages, different solvers for the partial differential equations, all these things. So very out of left field, very hard. The thing that I would say relating to your point is that don't be scared of that.
Yeah.
If you're confronted with a research project that just seems so far out in left field, that is difficult and kind of hard to think that you'd be suited for it, and you get imposter syndrome, just know that that happens to everybody. And you're not going to be as good as the guy who's been doing it for 30 years, but that's okay. Just do your best, do the tasks that are set out for you every week. Don't skimp out on doing the work. Show that you're committed to it, and learn and do your best, because it'll help you grow as a person. And trust me, it's worth it.
Yeah.
So.
No, I second that completely. I think for me, it was like, it's not just not being scared of it, but like embracing that and like really leaning into it, because you're not going to be as good as the person that's been doing it for 30 years because you haven't been doing it for 30 years.
Exactly.
You just started learning all of this stuff, and you're completely new to this whole like project and concept and idea. It's like you have the foundation skills, and these people have trusted you to be a part of this project for a reason. And so even if it feels like, well, I don't know everything, it's like you're not supposed to, and you don't, and they don't.
Right.
And you can only learn more by doing it. Like, you can only learn enough to be the person who's been doing it for 30 years when you've done it for 30 years.
Yeah.
And so, yeah, for sure, to just like lean into that like fear and just like really embrace being a part of projects that are hard, because they're often, I feel, the most rewarding projects too. You get the most out of a project that you're maybe intimidated to start.
Oh yeah, for sure.
Yeah. With that, we're going to segue into our first segment on the show. So this first segment is called Should We Be More Worried About? And so in doing public science communication and just kind of being aware of the sentiments I feel in the public about things that are scary in science, I've compiled lists of things that I think people maybe are more or less concerned about than they should be. And then I invite somebody on that I think has something to say about it or has some expertise in that field to address it. So for you, my question is, should we be more worried about advancements in optics related to mass surveillance?
Right. Yeah. So it's an interesting question for sure. And I think in terms of optics, there's a couple different ways that there can be mass surveillance. I mean, you can see in countries that are maybe a little bit more authoritarian, you have a couple different ways that we can use optics to survey different groups. I mean, for instance, if you look at like China, right, you could say that there's drones, right, that have cameras on them, and you can look and see. You can even look in multiple different spectra, which is interesting, right? Where the advancement of things like drones, the advancement of things like telescopes, where you can look in multiple different spectra of light, which means that you can see heat radiating from sources. You can look and see if there's devices that release certain spectra of light. Then you can see it right through someone's pocket, right? Let's say. So things like that. Should you be worried about it? I think that's more of a question of who has the technology, and whether, because the technology is going to be developed at some point just because of advancement of technology, how things are going. And I personally don't think advancement of technology is ever a reason to just be worried outright. That's never how I think about things. I think that, if we're going to create better optics and like the the most controversial take I have about this is that, splitting the atom wasn't inherently a bad thing, right? That it wasn't something that ultimately had to lead to a bunch of people dying, right? It was just the advancement of technology. And because it happened during wartime, you could say that was the major evil, right? The major problem is that, of course, we had to develop a bomb because, it was wartime. Bombs were going to be developed during wartime. That's a take that you could have. But splitting the atom itself, was energy, and energy is great, right? So creating optical devices and increasing the technology related to optics and increasing resolution, let's say, that you could have with cameras and, optical resolution when it comes to telescopes and, LiDAR technology, GIS technology, which is, geo informational technology when it comes to like surface mapping. These are all things that I believe should be developed more, and they will result in more surveillance. And I think the only thing that's going to lead, if it's like something you should be worried about or not worried about, is if now it's going to be used in the wrong way. And I think that's going to end up being a policy thing. It's going to end up being, up to regulation and things like that, like how it's always been for years and years to keep those things under bay. Will it be harder? Maybe, but also the technology related to keeping those things in check will also be more advanced, right?
Sure,
So,
yeah.
We'll be more interconnected, for instance. So we'll know when things are being used against us poorly easier, as long as those systems are put in place by, let's say, the government, right? So if the government allows us to know about projects, then we will know about them and we'll be able to see when they're being used poorly. If the government doesn't allow us to know about such projects, then that's a whole nother discussion.
Sure. Yeah.
But the projects themselves aren't necessarily, in my opinion, something you should worry about. But the policy surrounding it, maybe.
Yeah, I think that's a great point because you made a lot of great points.
Mm-hmm.
And I think, to me, there's always this weird tension between, especially with physics, I think, on the forefront of physics, between making discoveries that can be used to do bad and whether that should still happen for science or whether it shouldn't happen for politics. And so I think, like, something like you said that I really agreed with a lot is, like, it really depends completely on whose hands it's in. And I think something to go along with that is, like, in order for that discovery, for it to have been better that we did not make the discovery or we do not continue with those advancements, everyone would have to agree to not do that.
Yeah.
Right? And so it's like you're saying, really the only way to combat it is to continue to advance the technology that detects those things and that can like inform us about when they're being used and how, as opposed to stopping the advancements altogether, because not everybody is just going to agree to stopping those advancements.
And I genuinely believe that communication is a huge thing that everyone needs to consider when we increase our technology, because, you know, when we had, you could say, like, prehistoric technology, something where you're just like making a stick, right? Then you didn't have to tell your neighbor, I made this stick, right? Because it's so advanced, and I'm, you know, there's a possibility that I could come and kill you all with it. You're not gonna, you know, like prepare your neighbor for the fact that you have a stick, right? Because they could get a stick. Right. They could just go to their local tree and get a stick, right? But now, as you get more and more advanced, right, as you know, as so many barriers are put up to knowledge, right? You have to go through school, right? You have to study so many textbooks, right? You have to, you know so many things before you can truly understand technology. Now you really do have to communicate with people that don't specialize in those things. And tell them exactly what you're doing, and exactly what this technology is that you've just created. And I truly believe that is one of the reasons why people would fear something like surveillance technology, because they don't understand it. And that's okay that they don't understand it. No one should be a specialist, or not no one, but not everyone has to be a specialist in surveillance technology or lasers or, you know, physics in general. But I genuinely believe we do have to prepare people more for technologies that are coming out in relation to those things. Because if we don't, then it's, you know, those people will genuinely start to be fearful of it. And that's not fair to them.
Yeah, and I think, like in preparing people, there's a lot that comes into play with, like, education and being able to make sure that, like, physics in general is not scary to people. And I think that because a lot of people are intimidated by the math, by the concepts, by how much work you have to do in order to learn it and to learn it well, that I feel like there are so many barriers to that people just give up before they even get started. And I think, I don't know, I'm also hearing in what you said, like, that it really matters who has these things, and it's not just then what countries maybe have it or what organizations do, but also who has access to that knowledge, right? But I think, it's who. There's so many questions about who is doing what, right? And it's like what is the motivation behind something? Because I think your hot take about the atomic bomb is interesting to me, because I think largely I would agree with it, and it's interesting because I think it's hard to really separate, like, what is the point of building a bomb if not to bomb people? Right. But at the same time, it's like the point of the thing wasn't to be a bomb. It was to discover if we could do this thing, right? If this thing is physically possible, what the results of that were. And while it was heavily predicted by theory at that point, it's still, like, not proven until we can also show it experimentally. But it's like that only got the funding and attention and materials that it got because the motivation was to bomb people.
Right. And I would say, to add on to that, because I read a book called The Making the Atomic Bomb. I totally forget the author's name because I'm so bad at remembering authors' names. But basically, I mean, this was an 1,000-page book that detailed out everything from start to finish, and start meaning, like, you know, the moment they split the atom. Or actually the moment they discovered, like, neutrons and things like that, to, you know, the bombing of Hiroshima and Nagasaki. And so during that period of time, you can really see the struggle with the scientists involved, where it wasn't just, oh, we need to bomb our enemies. It was, starting off, we split the atom. This is limitless energy. This is amazing, right? We can do so many things, right? Nuclear fission, and then fusion was also almost immediately thought of. I mean, the possibilities with limitless energy from the atom were definitely thought of almost immediately.
Yeah.
But then developing from that, once World War II started, because splitting the atom and things like that happened before World War II, right? And it was kind of like this peaceful period, in quotes, where you had scientists from all over the world that were actually talking to one another. So the Japanese were talking to the Americans, the Germans were talking to the Americans and the British, and this actually a lot of early development on atomic technology was done by all these different scientists just sending letters to one another. Then the war starts, and all of a sudden now they're enemies. They can't talk to each other. Yeah. But then they also have this dilemma. The American scientists have this dilemma that they just believe that Nazi Germany is evil, yeah. right? And they kind of have it in their mind that Germany is going to develop the bomb first, and how do you stop that from happening as a scientist who number one goal is to create, something great in science, something that actually advances technology. But number two goal is to make sure that you don't die from an atomic bomb dropped by Germany.
Yeah.
Plus, there's the other aspect where a lot of those scientists were Jewish people who fled Germany during the 30s and the early 40s. So there's also some resentment, obviously, towards Germany in the minds of those scientists, and rightfully so. So they come onto like projects like the Manhattan Project and things like that, developing technology in nuclear physics, and then eventually it leads up to the point where now they have a bomb, and the government has taken over. Yeah. And they weren't fully out of the process. There were a couple of physicists that were in the process during the times when the bombs were dropped, but there was a large majority that were still kind of like, I don't know if we should kill a bunch of people with this, but we did make it, so that sucks. But there was the point is that the advancements of technology is a complicated thing. It's normally not just this is bad and this is good, and almost everything can be used for nefarious purposes and for good purposes. I mean, the advancement of the computer, right, made it so much easier for stalkers to reach somebody, or for serial killers to connect with their victims and to, connect with other serial killers, which may motivate them. So you could say the internet is a terrible place. Right. A lot of people do. You could say that, all advancements in rocketry are terrible because a lot of those advancements are used for military purposes, even though they're supposed to be explorational. Yeah. Eventually, a lot of things from NASA filter down into other military purposes. So I think it's a very complicated question. Yeah,
no, for sure. And it's like there's so many other questions that then come up that go into it of like, right, like who like is working on the project, what are their motivations, who has access to the results from what they're working on, and what are their motivations, right. And like, yeah, where funding sources are coming from, where like there's just so much that goes into it. But I think to me, one of the big takeaways of what you just said too is like, it was up until the war that communication was happening and active between scientists. I think scientists, generally speaking, are interested in sharing their results.
Oh yeah, no, they were so much in pain.
Yeah, like we're all nerds, and we just want to talk about the things that we're like nerding out about. Yeah. And so I think like when you go to conferences and stuff, for example, like if you gave somebody the light of day to talk for as many hours as they could about their project, they would absolutely do it, right? Yeah. Like we love talking about the results that we're getting. We love sharing them. That's like so fundamental to science. And so it's when other like motivations and other factors get involved that shut those channels off, that it becomes out of the hands of what science can do and what scientists can do, that it becomes dangerous, I think. But that was, incredible, comprehensive, and a really difficult question.
It is. But it was good. It was a good question.
Yeah, thank you. So with that, being said, we are going to take our first break. So everybody stay tuned and we'll be... All right, welcome back to WFNP 88.7 The Edge, Rosendale. This is continuing with Curiosities of the Cosmos. I'm your host, Allyson Sheneman, and I am joined by Jacob, a senior and student of physics and astronomy at SUNY New Paltz. We had a great conversation about research and bombs and everything in between, and we're going to continue now talking about what it's like to change fields and change interests. So you've told me before you went to a high school that specialized in film, and you were really interested in directing. Can you talk about what it was like to go from that high school environment to physics and astronomy in college?
Yeah, so the high school I went to was called Academy for Careers in Television and Film. It was this high school in Long Island City, which actually surprisingly isn't on, well, it's on Long Island because Queens is on Long Island, but it's not in Long Island, what is currently considered Long Island. It's on the East River, and it's this, so it's this neighborhood that's just at the edge of Queens near Manhattan, basically. It's on the other side of the river from Manhattan. You could say right near like Astoria and things like that. So the high school did focus on film. The way that it was structured is in ninth grade, you would, so I guess in freshman year of high school, I always say ninth grade, I do the numbers, which is weird. Not a lot of people do that.
I do too, because by the time I say freshman, I'm thinking college now. Like you can't, yeah, it's weird.
Anyway, so in freshman year of high school, they would, send you around with little camcorders, and they would make you do little projects and stuff. I remember I did like Star Wars when it came out. Oh no, that was in sophomore year. Anyway, point is, you would do like little projects filming, and then in sophomore year, it was like a step up. So instead of just working on your lonesome in ninth grade, you'd have like a 1-person team or a 2-person team, something like that. Sophomore year, they'd give you like 5 to 10 people or something like that. And you'd go and work together as a group. You'd still have a smaller camera for some instances, and then for other times you'd have a bigger camera, more production size, but it's still one of their smaller cameras that you would use. And you do things like, again, for our project it was Star Wars when it came out, the 7th movie or something. And I was super excited because Star Wars hadn't come out in a really long time. So I was like, all right, I'm going to film the opening, and we're going to do a documentary about the opening of Star Wars, which, for me was really cool. So that was fun. The teacher hated it. She thought it was the worst project she had ever seen. She took like one, and I was so sad too, because like I had edited the whole thing, and like I'd taken so much time, and like whatever. She took like one look at it and was like, this is garbage. Yeah.
What it's like to be creative.
But the teachers must have liked me to some extent, though, because so in 11th grade, they split you up into cohorts, which is just a fancy way of saying you get different assignments for your class section, basically. So we had a director's cohort, we had a camera cohort, a sound cohort, a set design cohort, and a like a dress cohort. I forgot what that's called. But they do up like all of the people's like makeup and wardrobe and makeup, right? Yeah. So that was another one. And all together now, you'd have 30 people working on a film instead of like 10 people working on a film. And I was part of the director's cohort. And really the only people that got into the director's cohort were people that the teachers thought had some sort of talent for directing. They wouldn't allow you into certain cohorts unless they thought that you had promise in those cohorts. So she must have not hated my project that bad. Or if maybe she did, but everyone else was like, calm down.
Right.
It's okay. But yeah, so then in junior year, the teachers would kind of guide us on certain projects. We did kind of a big horror movie type project. We did like a drama one. We did a chase scene. So we'd use all sort of things like dollies. So if you're not familiar, it's kind of like a cart that you put the camera on so you can have nice smooth movements while you're moving the camera. So, you can run with the dolly down a hallway, but it doesn't look like you're shaking. Like we would do sometimes like shoulder mounts, but that would be on purpose. Like if we wanted the camera to shake while you're running someone to make it look like you're the POV of someone chasing someone, then you'd have like a shoulder mounted something. Right. But if you just wanted to film both of them, let's say chasing down the hallway, the runner and the person chasing them, then you might use a dolly beside them. Then you'd have a nice smooth camera angle of them running down the hallway. So yeah, we had a lot of different things. Of course, with all the different cohorts, we had professional lighting, we had grips to manage those lights, we had a sound cohort with boom mics and all that stuff. It was very professional. And I was, basically I would write scripts for these films. It wasn't just like presented to me all the time. Some of the scripts were presented to me as like, this is what you're going to act out. And then other times it was like, write your own script for this project. For junior year, it was usually very small projects that I would write my own scripts for. The bigger ones, they would write it for me. Then senior year comes, and it's like you get all these big projects that you have to make completely by yourself. And so very hands-free. The teachers would like show up sometimes on set if they wanted to. But for the most part, you just wrote your own projects. I would write like 30-page scripts, which is a 30-minute film basically, and have to shoot them, multiple times a year. We would do things like that. And it was really cool. I had a really great experience. It gives me a lot of leadership skills. And it really broadened my idea of what I could do work-wise. And this is kind of the start of when I thought I could do physics. I would say it's like junior year and senior year of that. Because before that experience of like knowing how much work I could put into something, I was very unsure of what I would do in my life. I had watched a lot of documentaries, Nova documentaries when I was a kid on PBS, and those documentaries got me interested in science and astronomy and physics, but I never really thought that I had to be pressured into like making it something that I pursue, It was always like, oh yeah, I like science. Yeah, I'm like that dinosaur kid. I like dinosaurs. I would go to the Natural History Museum all the time as a little kid, and I would always run to the dinosaur section. I was that kid. Yeah. And I watched like this dinosaur documentary on repeat when I was a little kid. I had my favorite little dinosaurs. And I for some reason, I hated when the mammals came on. I don't know why. I was so like I was like a lizard supremacist or something. Yeah. Yeah. They were like too small for me. I was like, what's going on? These guys are not it. Anyway, so aside from that, right? I really, and then I would watch like Star Trek as a little kid. My dad was a huge nerd, so then I became a huge nerd. As natural progression. Yeah. Right.
As all things should be.
I mean, as I kind of alluded to, I really like Star Wars. So I would Star Wars, Star Trek, Battlestar Galactica, all these things all take part in space. So I was really fascinated in space. I love space for the longest time. I love physics for the longest time. But again, it was never something that I felt like I had to study in order to pursue at some point. Like I didn't really think of career until junior and senior year of high school. And then at that point, I was like, okay, I need to figure out what I'm studying in college, and I don't want to study film. Okay. Because it was just not my passion. Although like I had a great time and I felt like I was very suited for it and it gave me a lot of leadership skills, it was just not the thing for me. And transitioning from that into physics was painful. Yeah. To say the least. I knew I could put a lot of work into something, but I had no idea how to make it efficient when it came to studying something like math or science. Because I could stay up for hours and hours. I would stay up like all night a lot of times studying in freshman year of college, but it would go nowhere. I would study the blankness of a page type thing, like I would study one question for 8 hours. Yeah. And it would get me nowhere because I wouldn't cover the 3 other questions on the test. Yeah. So my efficiency was terrible, and I ended up getting pretty bad grades in freshman year. My GPA was very low. So yeah, I mean, it was rough. I think the only thing that really got me through it was I'm a very stubborn person. You know, that's kind of just the truth of it, where I set my mind to, like, I had a lot of time figuring out what I wanted to do in junior and senior year, of just like sitting down and being like, okay, this is what I'm interested in. This is what I'm going to do in college. This is what I'm going to do for the rest of my life. Once I like committed to that, it was like, oh, I'm getting bad grades. Whatever. You know?
Yeah.
And everyone else was like asking me like, are you sure you want to do this? Like, you really don't have any math or science. Like,
you were like, wait until I prove you wrong.
Yeah. You know? No, I mean, it was bad because it wasn't even like I wasn't even like building up animosity toward the people that doubted me. It was more just like I just ignored it, just straight up ignored it, because I was too focused on like what I was doing to care at all about what like anybody else said, which is like.
And you had no sleep to work off of.
And I had no sleep. Like, yeah, exactly. I was like caffeine driven. Like, get out of my face. You know. Yeah. But yeah, I mean, like, that's obviously like the advice I would give somebody else in my situation as well. But that's not an easy thing to do, and I acknowledge that. Yeah. It obviously depends on the type of person you are. It depends on your situation. Not everyone could just like push everything out of your way and like bury through brick walls to get to where you want to go. But the advice I would give is that it's totally possible. So whatever you have to do mentally to get yourself into the frame of mind of like completing that mission, you know, just like go and do that. So that would be my best advice, is that everyone says like you can do whatever you want to do when you grow up, right? But like no one acknowledges how painful that might be, right?
Yes.
That like they might look at you as a little kid trying to say like, oh, I want to be an astronaut, and they'll be like, yeah, you go do that, Charlie, right? But you know, but they're not gonna actually prepare you for the amount of effort that it takes to get to that point in your life. And the reality is you have to take every opportunity. You have to put all of your effort in, especially when it counts. Yeah. Because you can put your effort in certain situations and not in others, and those other situations might be the ones that it doesn't count.
Yeah.
And then you might fail, and you'll be like, why? I spent so much, I did so much effort, I tried so hard, and I still failed. It's like, you know, that you might have just not taken that one opportunity.
Yeah. You
might have just not done that one thing, and that's okay. Just do the next thing. Right? Because if you don't do the next thing and the next thing, the next thing, and the next thing, then someone gave me this really good advice. I don't remember exactly what it was. They said, opportunities come a lot. Like, there's so many opportunities you're going to have in your life, but they don't come, you don't get a lot of second chances, right? So you'll get a ton of opportunities, but once they pass you by, you're not going to ever have them again. So eventually, you're going to exhaust that pool of opportunities. So you just got to keep taking them. Yeah. But anyway, I'm done with my spiel of... But a
little motivational speech for everyone.
Motivational speech, yeah.
Yeah. No, that's so... You said so many things that are interesting to me there. I think, like, something that I think of immediately is just, like, I think it does take being stubborn to be in science. Everybody has to be a little, right?
Just a little bit.
Yeah, because you have to be so resilient to the fact that you will fail. Yeah. There is going to be failure. And for me, that was a really tough transition to make, because I went to a school. It wasn't a specialized school in a specific area, but it was an international baccalaureate school. So I was taking all like the most advanced classes that you could be taking. And I was like straight A student, right? Like I had a weighted like 4.3, 4.4 GPA. Like I was like so like focused on grades. And when I came here, like I had a rough transition because of the pandemic, I think, also, and moving online. Like my brain I cannot learn things in online classes. It just like does not work for me. But I think it's also like in that period where I was starting to hear this, like, are you sure this is what you want to do? Like, you could do something else, you know? Like somebody said to me, like you are taking college on the hardest settings possible. And I was like, yeah. And I won't change my mind. Yeah. I'm not going to do anything about that. Yeah. And I've had advisors be like, you can't do this double major because astronomy and bio just don't overlap enough. There's just not, like, it would take too long. You're going to have to graduate late. And I'm like, what if stop talking to me? Yeah.
Too bad.
Yeah. What if I did it anyway? Yeah. And I think there is a part of science that you just have to be that way. And obviously you should listen to advisors, and you should listen to people who, when they're saying, should you do this? Do you want to do this? Are you sure about this? You should second guess it a little, right? You should kind of go, am I sure about this?
Yeah.
And if the answer is immediately yes,
Then
I
you're
am
fine.
sure about this.
Yeah.
Yeah, stick with it, right?
Yeah.
Because there's a light at the end of that tunnel. And I think this is a perfect time, I think, for us to be having this conversation because we're reaching that light at the end of the tunnel, right?
Yeah.
And it's like, obviously it never ends, but just this like, this feeling like we both got into graduate programs. We're both doing the things that we want to do.
Yeah.
We've done plenty of research projects. Like it works out to freshman year us
Yeah.
who,
Yeah, exactly.
who felt so like burnt out and lost already and like needed that like stubbornness to get through, that we can now be like, it was worth it. It works out. Like everything works out. And I think the other part of it is that I think all scientists were dinosaur kids.
That's what I'm saying, y'all. Everybody I talk to is like, yeah, me too. And I'm like, man, that's so funny.
This might be, if I'm remembering correctly, this is like the third time that it's come up on the podcast.
Oh my God.
Like, when you said it, I was like, I got another one. Like, yes. I am so convinced that all kids who like dinosaurs should grow up to be scientists.
I gotta get all my little cousins in on dinosaurs. Well, I have reasoning for, I think, the natural progression why it happens too.
Okay.
I think that because dinosaurs are one of the first things that they introduce to kids that are like this kind of wondrous thing of like, these were like monsters that inhabited the earth, millions of years ago. And you're like, oh my God, millions of years ago? Like, number one, it's like they're monsters. Number two, it's like the earth is at least millions of years old, right?
Yeah.
It's like what goes through your head as a little kid. It's like, right? So you have this number that you barely just learned, right? Like, you don't even know what a million is.
Yeah, it's bigger than the numbers you know.
Right, exactly. You don't even know. You just learned 1 + 1. Like, so you're like, what is going on? So and then you're introduced. Maybe your parents give you that documentary, that you can watch that is maybe a little bit above the what you can understand, but maybe that just sparks something in you. And I think that's how it was for me, where it's like, just the wonder that it created with me was great. And then as I progressed, as I got older and I truly got into like these other concepts like physics and astronomy, then I was like, okay, the dinosaurs are cool. I love the dinosaurs, but physics and astronomy, just a lot bigger and more wonderful in my opinion.
Yeah.
Which, again, isn't to harp on the dinosaurs. And I think anyone that's like a paleontologist is absolutely fine.
Yeah.
Because that's what they find enjoyment in. But for me, the thing that gave me enjoyment was always seeking the bigger wonders, always asking the bigger questions. And I think that's why I enjoyed physics and astronomy. Whereas a kid, the big questions were, oh my God, what are the dinosaurs? And now it's like, oh my God, like, what's dark matter? What's, what do little particles do? What do elementary particles do in their natural states? What elementary particles can we create? What, like, particle physics is very interesting to me. Optics is very interesting to me because it's kind of a conjunction of a lot of different fields. You can do particle physics with optics. You can do thermal physics with optics. You can do so many different things. So, yeah. Yeah,
for sure. I mean, like, I just feel like you're so right that I think, like, dinosaurs are like a gateway in that way. Like, it's like you start out, it's like the first science thing that you do as a kid, right? It's like learn about dinosaurs. And I think at that moment, you either decide that is so not for you, or you fall in love with like the scientific like process and like the things that would lead you to being interested in something like astronomy, where it's like realizing how much you just love learning about that type of thing, right? And what it takes to learn that. Like, I remember when I was in elementary school, like, I was probably in like first grade. People were like, what do you want to be when you grow up? And I was like, a paleontologist.
I literally did the same thing.
Yeah. That's what I'm saying. Like, any kid that says paleontologist at like 6 years old, put them on the PhD track already. Like, they're already here. And it wasn't until like high school where I actually sat down and evaluated like, what is it specifically that I want to do? But in my mind, there has been zero doubt ever that it's science. Like, I think I always knew like that was what I was interested in. I was like, that was the thing that I wanted. And I think I had a similar epiphany where it was like, like, oh, I love dinosaurs. I want to be a paleontologist. And then I was like, but that road ends somewhere. Like, what if I did something that like never ends and it's like infinite and all these
always
like
spooky.
Yeah, exactly.
Yeah.
So yeah, I feel like astronomy and physics in a way is like dinosaurs for kids, but for adults.
Yeah.
Yeah.
For sure.
So yeah, with that being said, we're gonna move into another little fun thing about science, and we're gonna talk about fun facts.
Oh.
So this is our next segment called Curiosity Corner. So I'm going to tell you fun facts, 3 different fun facts, and you can rate how mind-blowing they are to you on a scale of 0 to 10.
0 to 10, okay.
0 to 10. Where 0 is like, it's either not fun or like you already knew it, and it's like, what even is that? And 10 is like you're going to think about it every second of every day for the rest of your life. Good or bad.
Okay.
Yeah. All right, so our first fun fact, because I literally know that every scientist is a dinosaur person, is about dinosaurs.
Oh God, okay. Yeah, of course.
Naturally.
Yeah.
Because this is the first time we've ever talked about dinosaurs, and
Yeah.
yet I knew. I was
course.
like, it's got to be, right? So the first fun fact is, in 200 million years, Earth days will be 25 hours long. Just bear with me there. About 70 million years ago, in the late Cretaceous period, which is where you think of like T-Rexes and everything, days were only 23 and a half hours.
That is very interesting. I would say that's like it's like a 5.
Okay.
Because like it is mind-blowing to think of the time scales, in my opinion, being that small.
Yeah.
Right? Because I mean, I guess it's not too small, but I know that because of, obviously the way that things move in our solar system, because of the tilt of the Earth and things like that, you're going to have a lot of shifts. I mean, even the polar shift where our poles swap. I mean, that's more due to just magnetism and stuff. But the idea is that, things shift around in the solar system. It's not too mind-blowing to think that our days are also going to shift a bit just because of the way the gravity works within the solar system a bit. So
Yeah, and for sure. I mean, it's a part of the moon tugging on us and like slowing down our orbit.
Right.
And so there's definitely like some pretty basic mechanics that are involved in order to make it happen. But yeah, T-Rexes had half an hour less in their day than we do. So.
Also, I think the moon's going to become tidally locked at some point, right? I believe so.
I don't know.
Yeah. Well, there's
Probably.
the thing where the moon's going to move out, but I think at some point the moon's going to move out to a distance, and then also part of this, like the moon's like slowing the Earth. The Earth is also slowing the moon.
Yes.
So the moon's eventually going to become tidally locked, and then one face will just face us eternally.
So the moon is tidally locked to the Earth.
I don't think it's fully tidally locked.
Not fully. Okay. I was like,
so. I think we do.
because that's the reason there's the dark side of the moon, and that it like as it orbits us, its orbital period around us is the same as our.
I don't think it is. I could be wrong, but
rotation.
I mean, maybe I'm wrong. And
but
maybe
it is definitely moving out. Like
it's
away
definitely
from
moving
us
out, and
slowly.
I believe that it's not fully tidally locked.
Okay.
And
Yeah.
but maybe I'm
It's
wrong.
like
and
it's
viewers
like at
don't
least a
listen to
little
me.
bit tidally
It's
locked.
at least a little bit tidally locked.
We know what we're talking about.
Yeah, for sure, for sure.
All right. So a 5. That feels solid to me because I've gotten 0s and I've gotten 10s on the show. So that feels like a 5 to me. I'm good with that.
Okay.
All right. Our next one is about nuclear reactors because I know everything about how this conversation was going to go.
Yeah.
So nuclear reactors glow blue. If you've seen like them in movies, things like that, they glow blue because there are particles in them that are traveling faster than the light is traveling around them.
That is pretty mind-blowing, I would say. I didn't know that the particles were moving faster than the light was. Do you know which particles?
I'm not sure of the particles in particular, but I have a little bit of elaborating on that I can do for our listeners mostly, but maybe something that will help figure this out. So we all know the speed of light in a vacuum is constant. It is the fastest thing in the universe, and it is that. But obviously, as we know through optics and stuff, when light is not traveling in a vacuum, its speed can change, right? And so like, for example, if light travels through water, it goes at 3/4 of the speed that it would go traveling through a vacuum. And so in nuclear reactors, we are forcing particles to go at really, really high speeds and the light around them to travel through insulating mediums. And so as the light is slowing down, the particles that are traveling through those same mediums are actually going faster than the light that is there. Now, they're not going faster than the speed of light, right? They're not going faster than light can go through a vacuum, but they are going faster than the light that is also traveling near and around them. And so this causes this like blue glowing, which is called Cherenkov radiation, if you're familiar with that. And so it's kind of like, it's like what a sonic boom is for sound, but for light instead. It's like that.
Okay.
Like, sort of. It like hasn't quite gotten there. It's like, you know what I mean? It's like the thing right before it can catch up to that.
That's interesting. Yeah.
But yeah, that's why they glow.
Yeah, that makes sense. I mean, that makes a lot more sense. Yeah, I'm not too familiar with Cherenkov radiation. I've definitely heard of it, and when I think of just radiation being produced in general, it's usually like energy shifts. So like something changes path, or electrons bump up in energy level or down energy level, more like down because of releasing energy, not gaining it. But things like that make me think of energy being released. So I'm not that familiar with exactly the blue hue, but that would make sense, I guess. In terms of the sonic boom aspect, I do know a lot about sonic booms.
Okay, elaborate.
So you mentioned that, and I was like, I don't know exactly how that would relate to the Cherenkov radiation, but sonic booms are interesting because it's like two mediums, or pressure mediums is the best way to think of it, like meeting each other. Right? So you have the pressure in front of the aircraft, and then you have the pressure build up behind the aircraft kind of meeting each other.
Okay.
And then that creates this loud because they're like two pressure mediums kind of like smashing into each other.
Yeah, the physics of the comparison there does not add up. Yeah. It's more the concept of like sound can do similar things, and therefore maybe it makes it easier to understand that light could also do similar things. But yeah, that's awesome.
Cool. All right. Is there a third one? That's
where I need a 0 to 10.
Oh yeah, my bad. Let's see. I would say a 7.
So, okay.
I'm a harsh critic, but that was good.
I'll take it.
Yeah, that was a good one.
Hey, 7. That's a passing grade.
Yeah. It's a passing grade. I know. I'd be a terrible physics teacher. I'd be like,
it's cool, but it's not that
right.
Cool.
You got the question right, but I felt it was wrong. So.
I just felt like maybe you didn't understand it, even though you wrote it in a way that made it seem like you understood it. Right, so I'm going to give you a 0.
I'd cross out the answer, write the wrong answer, and then cross it out again and write like -1.
For anybody who like writes in pencil, you just are erasing work.
I just erased the answer.
Yeah.
Why didn't you write the answer?
You did all the work right, but no answer. Right. 0 points. We can't be trusted.
No, we cannot. Don't make me a teacher ever. That's why I'm getting a master's and an internship in my program. I'm not becoming a teacher.
Staying away from education.
Yeah, I would be terrible for
untrustworthy.
Yeah.
Real. I know. I think I would make a good teacher. I just am scared to do it.
I think I would
Kids are scary.
Yeah, I would be a fun teacher up to a certain point.
Yeah.
I'd be like the fun teacher that's like happy-go-lucky when I'm teaching the material, and then come test time, I'd be like, well.
Yeah.
Like Jimmy would come over to me and be like, "Oh man, Mr. Beadle, you totally marked off like all these points on my test. Is there like any way that I can make them up for like the final? Like is there extra credit opportunities and stuff?" And I'd be like, "No."
There is a way you could have made it up. Learning the material.
Yeah. Right. No. I'd be terrible.
That's so bad. All the things that you've hated having in teachers.
Yeah, I know,
you're like, time to do that to
I'm
some
the
other poor kid.
Of trauma manifesting.
All right. Okay, we've got one more fun fact.
All right.
So, if you were to remove all of the empty space in atoms, all of the matter left over that makes up the human race could fit into the size of a sugar cube.
Wow. That is really interesting. I would say it's not super surprising.
Okay.
So on the surprising level, I would say like a 4.
Okay.
Because
You would make a bad teacher.
I would
Now I'm
make a
taking it
bad-
personal. I'm kidding.
I'm very familiar with how like much space is technically like within an atom. Like there's a lot of space in there, especially when you think of like the sizes of particles. The real reason why things, are like atoms don't necessarily like meld within each other and that space isn't used is because of all these forces. We have the weak force, the strong force, the electromagnetic force. And to do a little bit of elaboration on that for our viewers, because this is a science podcast, I don't want to just say things and not explain them. So the strong force is kind of this force that's held inside of the nucleus. And the weak force is held between kind of like these other interactions, these other, I think they're bosons. I'm taking a particle physics class right now, so you're going to have to excuse me. The weak force is complicated because sometimes it's also, you have the electroweak, so the electromagnetic force is a force between charges, and sometimes the weak and electromagnetic force are kind of talked about together occasionally. So there's that. And that's why particles don't just overlap within atoms and things. And actually when you touch something, so if like, let's say you touch a table, or you touch somebody else, or you touch their cheek, you're not actually touching the protons and the neutrons of those people. Your electrons are getting very, very, very close to each other. And then they're repelling because electrons have they have the same sign, so they're both negatively charged. So what that means is they're going to repel, because if you think of like a magnet, right, is the easiest way to think about it. It's very similar to electric charge. So if you have the same pole on a magnet, if you try to stick them together, they're going to repel. So it's the same thing with the electromagnetic force, where if you try to put two electrons together, they're going to repel off of each other. So that's actually what you're feeling when you try to touch something, is you're feeling all your electrons pushing back on you. So, and then, awesome. Touching a solid versus like water, let's say, all that's happening is there's so many more electrons close to each other because of the density, so the structure of that solid, that you're pressing up against more electrons, so you're feeling more strongly of an electromagnetic force. So depending on the structure, the internal structure of the thing that you're pressing up against, you're going to feel different surfaces. Different textures.
Awesome. Yeah, I think that I'm happy you included the like particle perspective on that, because I never feel quite confident enough to talk about it, because I didn't have to take particle physics. Mm-hmm. And so I never quite feel comfortable enough being like, this is something that I know about and I could explain to people. But I think it's so fascinating when we can kind of like zoom in that much on those things, because like immediately when you said that, and I would assume the same from our listeners, that you said like as soon as like you're like, when you're touching things, it's the electrons repelling, immediately you're compelled to be like go
what
feel
is going on?
Yeah, exactly. Because we just so can't think on that scale. Yeah. I just think it's awesome. And I think it does, like for me, the like human matter into the size of a sugar cube, like that's kind of me pulling both then like physics and bio together, because you think of like people as being so like all encompassing, like we're everywhere on the like globe. It's hard to find a place that there aren't people in the world. Right. And so it's crazy to me to think that we can have billions of people, and yet atoms have so much more empty space than what we could ever realize, that even though we have so many people, it's still like such a small amount of actual like things there. Right. And not just this like emptiness of space. And to elaborate on that, a little follow-up little tidbit for that one. If you were to force all of those atoms together and remove all of that empty space, a single teaspoon of that would weigh about 5 billion tons, which is about 10 times the weight of all of the humans that are currently alive, which I believe is also comparable to that of a neutron star, which is kind of it's the same like premise really there of like trying to get all of that matter in a much more compact space, right. And therefore, etc.
Right, and if you think of what a neutron star is doing, for anyone who's familiar with astronomy in the simplest sense is that stars, they're doing a lot of fusion, and neutron stars especially, their density is so large, so the atoms are scrunched up so much, and they're doing a lot of fusion. They're constantly active. So, you know, these stars, they're so compacted that you are going to get so massive even at a small scale because there's so much stuff in a small space. They're so dense. It's just very interesting. And, you know, think of fusion in general is this prospect of kind of getting past that electromagnetic force and actually overpowering it, and even getting and creating that strong force out of not nothing, but, you know, you have to put so much energy to make sure that, like, if you're wanting to create, you know, helium out of some hydrogen, you have to create that strong force. Yeah, it's interesting.
Yeah. Well, that is our last fun fact for the segment. So with that, we're going to cut to our last break. So stay with us and we'll be right back. All right, welcome back to WFNP 88.7 The Edge, Rosendale. This is continuing with Curiosities of the Cosmos. I'm your host, Allyson Sheneman, and I'm joined by Jacob, a senior and student of physics and astronomy at SUNY New Paltz. So for our last few minutes here, and to end every episode, I ask my guests to bring on their favorite question that they've ever been asked. So Jacob, what is your favorite question?
So my favorite question that I've ever been asked was actually by my cousin. And to put this in perspective, this is my older cousin. He's older by 2 years. It was funny because after I told this question to Allyson in preparation, she had...
I really thought he was like 8.
Yeah, she thought it was like 8 years old. By the way, this is the only answer that I told Allyson in preparation. This is not scripted. Okay, to be very clear. But you know, anyway, so he had asked me this question where at first he said, "What if the moon hit you?" Is what he had first said to me, and I was kind of like, "What?" Naturally, I was like, what are you talking about? What if the moon hit? Because there's so many factors that, like, as someone who's done astrophysics, you can't just say, what if the moon hit you, right? Because in space, if you think of things in the way they actually are, then you're really hitting the moon, right? The moon doesn't really hit you. If you're out in space and you've approached the moon, let's say with a spaceship, right? Everything is done using gravity. Right, so if you have a spaceship and you accelerate to circularize Earth's orbit, so now you're orbiting like the ISS does, the International Space Station. Now you're in a circular orbit. What that means is you're using gravity to assist you to go around the Earth in a perfectly in quotes, whatever, right, circular orbit. And what that is really you're missing the Earth. So what circular orbits are is they're missing the Earth constantly. They accelerate towards what's called a periapsis. And then they hit that point, which is with the point that's closest to the Earth. And then once they hit that point, they'll then decelerate. Decelerate is a terrible word to use in physics. Everybody hates me for it. But the point is you're slowing down, sure, okay, away from the periapsis towards what's called an apoapsis. That's the basics of orbital mechanics, at least when it comes to that stuff, trajectories in space. You're using orbits and gravity to do all the work for you when it comes to space. The only time you're using your engines is when you're accelerating, right? So now let's say you want to go from Earth's orbit to the moon. Then you're going to accelerate so that your orbit breaks. You're going so fast that no longer are you just missing the Earth and coming back around, being tugged around by the Earth, but now you're missing the Earth so much that you're flying away from the Earth. And let's say now you have to go to the moon. You want to go to the moon. So now you kind of want to crash into the moon's sphere of influence. You're not going to try to crash into it directly, let's say. Not yet. We're getting there. Now you just want to interact with the moon's sphere of influence, meaning now you're going to go and try to have it tug you around. And so you're going to go to it, and then you're going to burn your engines again in the opposite direction. You're going to try to circularize that orbit with the moon. And you're going to try to get a circular orbit there going as well. Great. Now we have that. Now let's say I want to crash into the moon. Now I'm going to slow down more so that the moon tugs me down towards its surface. but then I'm going to be the one crashing into the moon. The moon isn't really going to be crashing into me. Right. My cousin's question, the way he wanted me to answer it was, what if the moon hit me like a baseball? Right?
Right.
Now, the way I've just explained it does not really allow for that scenario. Right? Because we're both moving in the solar system around the Earth, right? When you're in the moon's sphere of influence, you're also orbiting the Earth, right? And the Earth is orbiting the sun, which the sun and the solar system is orbiting the galaxy, right? And all of those things are happening at incredible rates of speed.
And the galaxy's moving.
The galaxy's moving too.
Everything in space, everything is moving constantly.
Exactly. So his question, once I got him to elaborate, became, what if we had no momentum? What if we were just standing still and the moon came and smacked us in the face? Right?
Sure.
And then I was like, okay, but as the moon approached, we'd be tugged towards it. And before that, we'd be tugged towards the Earth. And before that, we'd be tugged towards the sun.
Right.
And before that, we'd be tugged towards probably something else that was even more massive somewhere else.
Yeah.
Right? Because once we had zero momentum, we'd be tugged towards the body that had the most mass. That's the closest to us. And for all we know, actually, that might have been, it'd probably be the sun. But, maybe if Jupiter was, like, close enough, we'd be like, towards Jupiter,
Sure.
Who knows? But, yeah, you just immediately in a straight line go towards whatever had the most mass.
Sure.
That was near you. So you wouldn't even necessarily go towards the moon.
Yeah.
So I'm trying to answer this, like, fully, like, scientific. And he's just like, no. What if you took everything out of the equation? Okay, you didn't have the Earth, you didn't have the sun, you didn't have Jupiter, you just had like the moon in like a white room with you, like some blank like Matrix stuff.
Yeah.
And it just like
hit you in the face.
Mm-hmm. And like the obvious answer is you die.
I was just going to say, all he wants to hear you say is you're going to die.
But like he wanted to know like the biological implications of like what would happen to you if you smacked into the moon. And like here I am being like, well, I mean, I think we all know what happens, but like obviously
it would probably hurt.
But it's obvious, like I was trying to do my due diligence of like, obviously it would vary based on exactly how much we were crashing into the moon. Like if the moon just hit us, what speed is it hitting us with?
Sure.
Right? Because if he's throwing it like a baseball at me, are we saying that it's the speed that it's going around the Earth? Is it the centripetal, basically, like velocity that it has going around the Earth? Are we talking about the velocity it's had going around the solar system?
Or is it going the speed that a baseball typically gets thrown at?
Is it going at the speed that the baseball is typically thrown at? Like, which speed are we talking about? Because that really changes the equation here.
Yeah.
But
and
anyway,
how far is that person away from you? If they're throwing at the same speed as a baseball, but it's the size of the moon?
Right. That's a really buff guy.
And really far away.
And really far away, yeah.
Otherwise, you'd just be, like, you wouldn't throw at the same distance you would normally throw a baseball. Because you'd be really, like, you would already be in the moon by the time they're trying to throw it.
Goku over here throwing the moon at me. But, I mean, so obviously this is a really, like, silly question, right? But I think one of the interesting things about being asked a question like this, and why it's one of my favorite questions, is almost because of the silliness aspect of it. Because it just shows how someone who may not be super familiar with physics and science might frame their understanding of the universe sometimes. And like obviously to him it was probably a silly question too. He wasn't being very serious when he asked this.
Yeah.
But it was still like he hadn't considered everything, right? Yeah. Every possibility, and nor should he necessarily have to, because he doesn't study all of it.
Right.
But it kind of reminds me of this feeling that I had where it's like, man, like this is what my job is gonna be also. Yeah. It's like this is what we're here for. Like as scientists, we have to do our due diligence to kind of give all of the information, even if at sometimes it might feel silly, especially to us. Just give every possible bit of information out to everybody so that they can try to understand the universe in their own way. I mean, at the end of the day, we're kind of like mediators of the natural world, especially in physics, where the description of physics is just trying to understand the natural world. It's just the science behind the natural world. Yeah. And so is basically every other science. I mean, every science is just trying to understand the natural world to its own extent. But especially I feel like with my field, it's just, we're the interpreters. And it's our job to really try to, even when it seems silly, just try to give all that information out and really educate where we feel we can.
Yeah.
You know?
Yeah, absolutely. I feel like something that I really also wanted to do in starting this show, but the reason that I keep bringing back people in education on the show is because I keep thinking, how perfect would it be if everybody was equipped to be able to answer those questions themselves? And sure, when you get to questions like things that are on the cutting edge of where science is right now, where it gets more complicated to understand, sure, that requires specialization, right? And at that point, we do have to be intentional about how we communicate it, making sure that people become aware of what we're doing and why and what it means and all of those things. But it's not essential that every single person understands deeply particle physics.
Right.
Right. It would be cool if more people knew about it, and if that was more of a standard. But it's not essential for everybody to go about their day that people are just fine, right, not knowing about particle physics. But I think it would be so wonderful if those kinds of silly questions could be answered by the people that are asking them, and by friends that do not specialize in that field, because we are all equipped enough to know how those things work, right? You don't have to necessarily know orbital mechanics in order to answer that question. That, again, is maybe where I'm getting at with what would require specialization. But being able to just say, I have a sense of what would happen if these scenarios were to come about. And even in asking that silly question, knowing that you'd have to specify further before you could get into the physics problem of it all, right? And so I think, I don't know, it just also to me emphasizes the need to teach this stuff at a level that is useful for people to be able to problem solve on their own later in their lives, that you can ask silly questions, and we should all ask silly questions all the time. They're awesome. But to be able to start answering them yourself too, I think is I don't know, it's really powerful.
Even if it's just to the extent of everyone just knows some fun facts about physics.
Sure.
You know, even if you're a store clerk and you just have in the back of your head all these cool physics facts that you got from listening to a podcast.
Yeah.
You know, that is useful knowledge that, somehow may help you at some point. You never know.
And just
right?
in general, I think benefits quality of life. You should want to learn things.
Yeah. You may it might just make you more happy to know things.
Exactly.
And I think everyone should strive to be more well-rounded in general. I mean, I think this is it's not even just about knowledge, it's about hobbies and things like that, where it just helps to be the most well-rounded person in general, knowledge-wise, hobby-wise, everything. So the more you can learn about every single topic, no matter if you think it's stupid. I mean, you might think that, math is not for you or physics is not for you. But, at the end of the day, there are a lot of people out there that know it and you don't.
Yeah.
And, for me, that's intimidating when I hear that. When I'm like, man, there's so many people out there that know this subject and I don't know anything about it. I'll usually go on the internet and look up something about it because I'm I need to know at least something.
Yeah.
So I encourage people to do the same.
Yeah. And it's something that you can know about.
Yeah.
You know what I mean? I think we're both testaments to that. It can be intimidating, it can be scary, it can be hard to learn about it, but at the same time, if people can know it, then you can too.
Yeah.
Do you know what I mean?
For sure.
Yeah.
You definitely don't have to be smart.
Yes.
I think there's a total stigma. Maybe stick a fad.
Yeah.
Is what I would say. It's like a trend.
Yeah.
That people think about when they think of STEM in general and the sciences, where they think that you have to actually have an IQ that's high, or you need to be smart in general. And the amount of times that I think all of us have heard, oh, you study this thing? Oh, that means you must be smart, huh? You're Einstein.
Oh, you're
here.
smarter than me. It's
it's no, I'm not. I'll hear someone does something incredible, right? An incredible achievement. Some of my friends, they're really amazing hikers, right? They'll go and they'll do the Appalachian Trail or something, and things like that. And it's like, in my opinion, what I do in my life is equal, if not, less than some of the achievements they've done.
Yeah.
And, they might think the same of me, but it has nothing to do, in my opinion, with being smart or anything like that. Because it's, at the end of the day, it's all just like, you were smart enough to take initiative in your life and do what you like to do.
Yeah.
I'm smart enough to take initiative in my life and do what I want to do.
Yeah.
That's the only smart that matters, in my opinion, right? If you're happy doing what you want to do, then you're intelligent enough to, to live, Like, I'm not saying that everyone who doesn't do what they want to do, I feel like that's the wrong message to take from that, but
you're intelligent enough.
You're intelligent enough. Yeah. The point that I'm making is just, everyone should do what they want to do no matter what. And if that thing that you want to do is science, something related to science, physics, then don't let anybody tell you no.
Yeah.
Go and do that thing. Don't compare yourself to anybody. If there's some kid in your class that's doing a lot better than you, getting straight A's or something, then that's great. They're doing amazing. They're also on a path that is amazing and good for them. But don't ever let that discourage you.
Yeah.
And don't ever let you tell yourself that you're not smart because of things like that.
I think the hiking comparison is really powerful there too, because like I feel like I would never think of like somebody who hikes and be like, oh, that person, like, and somebody who could like complete something like the Appalachian Trail, this huge accomplishment, and be like, well, that person's smarter than me. Right? It's like, because that's not the basis that we're judging that off of, right? You could say maybe that person's more athletic than me. I don't know if I could do that,
right.
Something like that. But it's like, at that point, it's not like, oh, I am incapable of said thing. It is that is not where I have dedicated my efforts.
Right, which it should be for everything.
Absolutely. I feel the same way.
Yeah.
Because it's like, I dedicated my efforts to astronomy and bio, and you dedicate your efforts to physics and astronomy. And so therefore, we have put a lot of effort into really learning those things.
Right.
It's like, if you, as somebody who hasn't started that yet, isn't sure if you're going to start that yet, if you want to, or if you're just listening and you enjoy the subject, but you're not going to pursue that, it should never be like well, then you're not as smart.
Yeah.
Because you just haven't dedicated your effort to that thing.
Right.
You've dedicated it to the other things that you do. You know what I mean?
I mean, it's very funny because the same years that I was starting to like dedicate myself to the idea of like going and studying physics in like late high school, I was also really starting to get into fitness and doing a lot of pull-ups and climbing and things like that. So, I had an athletic body, and I, at every level, I looked like someone that was just like this jock kid, right? And it was funny because my aunt would like make fun of me, I like basically like call me a jock. Right. And like that comes with a connotation that you're also not smart. Right. That you're only good at doing jockey things. And I, again, like referring to the past, like if people said things like that, I mostly was just like, I don't care. Like whatever. Right. Sure. I never was one to like feel bullied by anything that anyone said, but things like that can definitely get to people.
Sure. Yeah.
For sure. And I think that that's one of the main motivations behind why people don't take up science, is because they'll hear something like that and they'll be like, you're right. I'm just this kid that does pull-ups and rock climbs occasionally.
Right.
I'm not going to go anywhere, right? This is the only path I have, which it might be. If you want to go rock climb and want to go,
there's careers
do a bunch of exercise,
in that.
there's careers in that. And again, I think you're very smart for doing what you want to do.
Yeah.
But if someone tells you that you're not smart because you want to go do those things, and therefore you shouldn't go do other things, because you're not smart enough to go do the other things, just ignore them. Just straight up just be like, oh yeah, you're wrong, bye.
Yeah. It's a beautiful message to close out on. So unfortunately, that is all the time that we had for today. So thank you again, Jacob, for coming on the show.
Thanks for having me.
And thank you all for listening. This has been your host, Allyson Sheneman, and my guest,
Jacob Beadle.
on Curiosities.